Imagine you have a bucket of sludge, 90% water and 5% solids. For dry thermochemical processes, this is a nightmare. You will have to evaporate almost all that water before you can even start. Wet thermochemical processes flip that logic. Instead of fighting water, they use water as the reaction medium. That's the idea behind hydrothermal carbonization and hydrothermal liquefaction. In this video, we'll see how these technologies work, what they produce, and how they complement dry thermochemical routes. Let's start with what happens to water itself. Hydrothermal processes are performed in one of two water states, sub and supercritical water. These states are defined with respect to the critical point of water. If we heat water to about 200 to 350 degrees Celsius and keep it under high pressure, it stays liquid, but its behavior changes a lot. Its dielectric constant drops, so it acts more like a low polarity solvent, and its ionic product increases, making it a very good medium for acid-base and ionic reactions. In simple terms, hot compressed water can dissolve waste and help break it apart and build it into new molecules. Hydrothermal carbonization and liquefaction both use this, but they push the chemistry in different directions. First, let's have a look at hydrothermal carbonization, or HTC. It treats very wet biomass slurries and converts them into a solid called hydrochar. Generally, the HTC process occurs at relatively low temperatures and under autogenous pressure that lowers both the oxygen and hydrogen content of the feedstock through dehydration and decarboxylation reactions. Under HTC conditions, water becomes very reactive and behaves more like an organic solvent. This combination speeds up biomass coal formation by roughly 2 orders of magnitude compared with natural conditions. As a result, we observe an increase in the energy density of the hydrochar from about 16 to 18 megajoule per kilogram for typical lignocellulosic biomass to about 22 to 30 megajoule per kilogram for hydrochar. But there are also trade-offs. Most of the ash, nitrogen, and heavy metals stay in the hydrochar. That's good if you want a nutrient-rich soil amendment, but less ideal if you want a clean fuel or a carbon material. The processed water is a different story. After HTC, the processed water often has very high chemical oxygen demand and is rich in sugars, organic acids, and humic-like substances. You cannot just discharge this. In many realistic process designs, HTC water is sent to an anaerobic digester, where part of the dissolved organics are recovered as biogas, and the remaining nutrients are recycled. So HTC is rarely a standalone process. It works best when tightly integrated with biological treatment and energy recovery. Now let's talk about hydrothermal liquefaction, HTL. HTL pushes conditions closer to the critical point of water. The temperatures and pressures are higher than in HTC process, reaching 374 degrees Celsius and 22 megapascals. The residence time ranges from 5 minutes to 1 hour. Here, we aim to convert wet biomass into a liquid oil phase, usually called biocrude. Under HTL conditions, water has a high degree of solvation with organic compounds, which happens due to the variability of the dielectric constant of water. It can solubilize lipids, lignin fragments, and depolymerize sugars. Reaction pathways include hydrolysis, dehydration, decarboxylation, and recondensation into oil-like molecules. For lignocellulosic feedstocks, biocrude yields are often between 8 to 36 weight%. For lipid-rich feedstocks such as oily microalgae and oilseeds, biocrude yields can reach up to 54 weight%. And for protein-rich feedstocks, biocrude's yield can go as high as 61 weight%. HTL biocrudes are comparable to fossil crude in terms of their heating value, which can reach up to 36 to 39 megajoules per kilogram. But biocrude is not a drop-in fuel. It still contains oxygen, nitrogen, and some sulfur. So it usually needs hydrotreating to remove heteroatoms and narrow the boiling range. From an engineering view, the hardest part of HTL is often the feed and product handling, not the reactor. We must pump a 5 to 30 weight% solid biomass slurry to pressures above 10 megapascals and keep it homogeneous. A common design rule is to keep the particle size less than 100 micrometers to reduce clogging. Preheating is critical. If the slurry stays too long at these high temperatures, side reaction can cause falling and plugging in heat exchanger. That's the reason tubular heat exchangers are commonly used because they are easier to clean. The aqueous phase of HTL is also rich in alkalis and phosphates, good for nutrient recovery, but has high chemical oxygen demand, ammonia, and total nitrogen content, so it is usually sent to anaerobic digestion or stripping. Finally, product separation is challenging. A hot, high-pressure stream loaded with solids and ash can easily block downstream units if not carefully designed. HTL is not limited to pure biomass. Subcritical water can depolymerize polymers with heteroatoms, such as epoxy, PET, and polyurethanes, at relatively low temperature and pressure. These weaker bonds around heteroatoms break more easily. However, simple polyolefins like PE and PP made of long hydrocarbon chains are quite inert and usually need supercritical water or catalyst or co-solvents, which makes the process much more expensive. To summarize, you can think of HTC as a way to make a coal-like solid from very wet, low-value feedstocks, improving dewaterability and energy density. You can think of HTL as a way to make a renewable crude oil from low-grade waste, avoiding the energy penalty of drying the biomass. Nonetheless, HTC and HTL demands clever integration due to concentrating wastewater. HTC and HTL don't replace dry thermochemical routes, they complement them. Hydrothermal processes are ideal for sludges, manures, and mixed waste where water and contaminants are unavoidable.